Example 4. So if f of x equals x cubed times 1 minus x to the fourth, use the second derivative test to determine if the critical points are local maxes, local mins, or neither. So we determined that the first derivative, once it's simplified, is x squared times 1 minus x cubed times 3 minus 7x. From there, we were able to get the critical points of 0, 1, and 3/7. So if we wanted to take the derivative of this function, we'd have to do a modified product rule. So it's a product rule, but then there's a product rule within the product rule. So I picked my f to be the first two terms, x squared times 1 minus x cubed, and my g to be the last term, 3 minus 7x. Now my g prime is just the derivative of g, which is negative 7. That one's straightforward. But to take the derivative of f, I have to do another product rule. And so I took the derivative of the first term to get 2x times the second, plus the derivative of the second times the first. But when I took the derivative of the second term here, I had to use a chain rule. So it was really quite complicated to get the algebra down. So then I have to do f prime times g. So my f prime is in this whole first bracket. It's this whole term that came out from the product rule times g plus g prime times f. I'd pulled the negative to the front to make it a little bit easier to see, but as you can tell, it's already a very complicated function. Now, once I have my second derivative, again, I want to plug in my critical points to try to determine if the second derivative is positive, negative, or 0. If I tried to plug in a 0, what's going to happen here is that this term, first term, is going to be 0. This term is also going to be 0 because of the x squared, and it's multiplying this. So this whole first part here is going to be 0, minus, and then this term's also going to be 0. So when I plug in a 0 into the second derivative, I get 0. So the test is inconclusive. Now, if I tried to plug in a 1, the same thing is going to happen here. Because the first term, this is going to be 0. This is going to be 0. Over here, this is going to be 0. So everything that's multiplied together ends up zeroing out. So when I plug in 1, I also get that the second derivative is 0 and therefore inconclusive. However, when I plug in a 3/7 really carefully, this term ends up being 0, which is going to zero out this whole first part. But the second term is not 0. Instead, I'll have 1 minus 3/7, which is positive. Something positive cubed is positive. X squared will be positive. So I have 0 minus something positive, which is going to give me something negative. So when I plug 3/7 in, I do get some sort of answer. I get that my second derivative is negative. And we know that if the second derivative is negative, that means that your critical point is a local maximum. So this type of problem, it's not really ideal to use the second derivative test. There are better tests that are easier to work with to determine if your critical points are local maximums or minimums, but it can be done. Although it didn't give us all the information that we needed. We were only able to really classify one point, but it's still better than nothing. So let's look at another situation. A situation where we have a lot of information we have to sort through to try to do some analysis and determine what we know about a function. Example 5. Suppose f of x is a continuous differentiable function. Additionally, we know the following information. So here we have a various amount of information about the function at points, the derivative at certain points, and the second derivative at certain points. And we want to use this information to determine where we think that f of x is likely to have a local maximum and or minimum. So we have to sort through this information to see what we can figure out. So let's look at each piece individually. F of 1 equals 10. So that's a point on your function that when x equals 1, y equals 10. F of 7 equals 1. Also a point. Points aren't generally helpful in helping us determine things like maximums and minimums. Now we know that the derivative at 2 equals 4. So that tells me that my original function, f of x, is increasing at x equals 2. So remember, we're talking about what's happening at 2 because 2 is the independent number that got plugged into the derivative function. The next statement says f prime of 4 equals 0. So that's really important because that tells me that I'm going to have a critical point at x equals 4. So remember, the x value is what's inside the function. So when we're talking about where things are happening, we're pulling the number that's inside f, not the one that it's equal to. Because when it's equal to something, that's giving you the slope of the tangent line when we're talking about the derivative. So f prime of 9 equals 0 means we're going to have a second critical point at x equals 9. Now I'm also told that the derivative at 12 equals 8, which means that my function is increasing at x equals 12. Now I have that the second derivative at 4 is negative 4. So if the second derivative at a point is negative, that means it's concave down. So I am concave down at x equals 4. And then I have that the second derivative at 9 equals 3. So if the second derivative is positive at a point, then I'm going to be concave up at x equals 9. So again, it's at 9 because 9 is the independent value that's plugged in here. So looking at the big picture now with all the things I know, I'm really interested in what's happening at the critical points because I know that that's where I'm likely to have local maxes and mins. So I have a critical point at 4 and a critical point at 9. But then I also have information about the second derivative at those points. So at 4, my function is concave down. So if I have a critical point at 4, and I know that the second derivative is negative there, and I'm concave down, that tells me that x equals 4 is going to be a local maximum. Similarly, I have a critical point at 9, and I also know that I'm concave up at 9 because the second derivative is positive there. So that tells me that x equals 9 is going to be a local minimum. So we have all the information we need to talk about where these things might happen, these local maxes and mins, but we have to sort through all the information we have and figure out what's relevant and just use those parts. The other statements here give us a little bit of information about the function, but not really about the critical point. So we have to determine what's important to use. Example 6. Suppose that f of x equals ax squared plus bx minus c, where a, b, and c are non-zero constants. What has to be true about a for this function to have a local minimum? So we talked a little bit about this function before, but let's recap. Our first derivative of this function is 2ax plus b. So if we want to find the critical points, we would set that equal to 0, and we get x equals negative b over 2a. But that just tells us about critical points. It doesn't tell us about whether it's a maximum or a minimum. And since we're in the second derivative test section, let's look at the second derivative to see if it tells us anything. So here, the second derivative of this function is going to be 2a. Well, that's really interesting because the x has disappeared, which means that this entire function is either concave up or concave down based on the value of a. If a happens to be positive, greater than 0, that means the entire second derivative is positive, which means for all values of x, your original function is going to be concave up. Whereas if a happens to be negative, that means that for every value of x, the original function would have to be concave down. Here, we want to know what has to be true about a for this function to have a minimum. So if this function is to have a minimum, we would need the second derivative to be positive so that the original was concave up. So a would have to be greater than 0 in order for this function to have a local minimum. And then we also know that it's going to happen at x equals negative b divided by 2a.